there are some other pump that is not a turbo machine. Remember last time I told you that this pump is not a turbo machine, because turbo is the word from Greek mean rotation. Turbo mean rotation. In this case, yeah, it is rotating, but the way the fluid moving is not due to the rotation, but it's more likely due to the pressure difference or displacement. Okay, if you have a piston like this, what happens is okay, when you suck, when you move it there, the air or the water will go here, right? When you push, when you suck it there, this one-way valve will close. So you will get all the water coming in. When you move it there, it open, it close, right? Or even there will be some valve installed there, right? Just a one-way valve. Why is this called positive displacement? Is because it moves there. When it push, then the water will go there. So this is the basic of positive displacement machine. In the case of those three-lobe rotary, right? When it moves, it will create a void there where the liquid will come in. When it rotates, it will push the water goes to that side. So the basic concept is same with this one. You are squeezing the fluid. Same goes for this one. See, when it moves, the water is trapped, and then you force it to move to the other direction. It is not due to the rotation. If you remove the tube, right? If you remove the tube and replace it with the blade, then you get a turbo machine. Because then the rotation is due to the rotation of the blade. But if you have this, you squeeze the flow, then it is called a positive displacement machine. The same goes for the gear pump. In the gear pump, you have a void there, and then you push the waters. Okay. So this is all positive displacement pump. Okay, but if you tell this to normal people, they will say, no, this one is still turbo machine. Okay. No need to argue with them. Just accept it. You know that this one is positive displacement machine, but usually they call it still turbo machine. So when you have a fluid sucked into an expanding volume and then push along that, this one is called a displacement pump. Okay? So now let's take a look into how to analyze it. Then the calculation will be there. Okay? So if you think that pump is increasing the velocity, you are totally wrong. Anyone here thinking that if you put the pump, the velocity will increase? Yes. How do you get the increase in the velocity? Increase in pressure is correct. Now, how many of you think that if you install a pump, you will increase the velocity? 1, 2, 3, 4. Oh, you too, eh? Okay. Why do you think it increased the velocity? Because it's pumped, yes. Then? How do you get the impression that when you install a pump, the velocity is increased? From what? I mean, you know, when I look at you, oh, you are pretty. Why? Because I see your face is pretty. That's it, right? Now, you think that the pump is having a capacity or capability to increase the velocity from what? How do you know it increase the velocity? Energy. How do you measure the velocity from the energy? And even I should ask you, how do you measure the energy? Bernoulli. Okay. You are talking about Bernoulli and you want the velocity to be increased. Okay, let's see. You do that. Okay. Bisa I buy. I accept your challenge. You have a pump. Right? This is your pump. This is the symbol of pump. This is your diameter. This is your diameter. Any one of you ever seen the pump that having inlet and outlet different size? The inlet and outlet of the pump usually is using the same size or different size? Same size, right? If you are having a pump with 3/4 inch of pipe, then the outlet will be the same. Correct, eh? Which means U1 is equal to? Okay. Do pump have storage? No. If there is no storage, what will happen? Is it the same? Okay. It's the same, right? Do your water compressible or incompressible? Water? You can compress water? Water is compressible or incompressible? Incompressible. So you have row here, row there. The same, right? You said yourself, m dot 1 is equal to m dot 2. Rho A, rho D1 is equal to D2. By right, your rho 1 is equal to rho 2, right? Yes. How come on earth you get V1 is different with V2? Huh? Right. You said M1 is equal to M2. You said rho 1 is equal to rho 2. Right. You said D1 is equal to D2. But then you said that V2 is higher than V1. How on earth that can happen? You know why you get the impression that when you put the pump, you will get a higher flow rate? Because in your daily life, when you turn on the pump, it is where the flow is coming. When you turn off the pump, there is no flow. So actually, you are not measuring the same thing, right? But if you are dealing with, let's say, you have a tap water there, okay, then you install a pump there. This pump will not add any velocity. The velocity will remain constant, right? The mass coming in has to be equal to the mass coming out, but the pressure will be higher. If the pressure is higher, you can squeeze it. You squeeze the hose, that's why you get higher velocity. So basically you get the impression of higher velocity is because you squeeze it. If you just do that, nothing will change. Given the flow is already there, but usually what happens is you don't have the flow without the pump. When you have the pump, only you get the flow. Okay. So basically this pump is most likely to not change the velocity. It will only change the pressure.